Section 2.1 takes everything that you've learned about finding limits and uses it to start developing the first of the fundamental rules that you're going to learn in calculus this year. We will be finding slopes of tangent lines to a curve to help us study what's happening at functions at an instantaneous point in time. We're going to use the limit definition to find the derivative of a variety of functions. And we're going to discuss the relationship between differentiability and continuity. So let's begin our discussion with the tangent line problem. We briefly discussed this at the beginning of the year, so let me just review it for you. We have a value of x and we look at the corresponding y value, and we want to study what's happening to our graph at exactly this point. Now, not being able to find out exactly the rate of change at that point, we go a little distance away and we say, okay, let's measure that distance by delta x. So that gives us a new point, taking our original x value, adding the distance we traveled, delta x, x plus delta x is our new x value, and we find a corresponding y value for that new x. And if we study this line, then we can find the slope, and we're familiar with our slope formula and the Greek representation of delta y over delta x. Plugging in our points, x plus delta x is our x2 and x is our x1. So plugging that in so that we get y2 minus y1 over x2 minus x1. Our x's in the denominator cancel, and it simplifies down to f of x plus delta x minus f of x all over delta x, but in the end, it's still just slope. So the problem is that if I want to actually know what's happening at exactly this point, I need to get closer. But no matter how close I get, let's say that my delta x now becomes very tiny. It's coming back close to my x, and I get a point that's closer. I'm still studying the change between 2 points. And that will always be the slope of the secant. What we really want is to study the slope of the tangent, because we want to know what's happening at exactly our point. So let's use our slope of our secant to lead us into our slope of the tangent. We know that our slope of our secant is average rate of change, which isn't good enough because we want to study what's happening at exactly this point, not just a few milliseconds away. We want to know at this exact second what's happening. And so we need to take our basic slope and look at it in the form of the slope of the tangent, because if I have a tangent line, then I know that my tangent line at that point shares that point, and the behavior of the line, the slope, is going to be exactly the same behavior at exactly that point. Not at any other point on my graph, but at exactly that point. And so I want to use the slope of the tangent because it will give me instantaneous change. Now, we've been studying limits. So what if we said our delta x is getting so close to our x that our delta x is approaching 0? Couldn't we take the limit of our slope formula, and then that would be the rate of change at exactly the point that we want? The formal definition of the derivative is exactly that if I want to find f prime, that's notation for a derivative, f prime of x, is equal to taking the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, provided that the limit exists for all values of x for which this limit exists, f prime is a function of x. The process that we do is called differentiation, and the function will be differentiable if all values of x exist and if the function is differentiable across our interval. So just a few technicalities before we get started. In the process that calculus was being developed, Newton and Leibniz, the two developers of calculus, couldn't agree on who actually discovered this process. And therefore, over the years, the blending of their notes, because they wouldn't work together, has given us an extra amount of notation to work with. So we have f prime of x, delta y over delta x, dy over dx, y prime, d dx of f of x, and dx of y. And all of these mean exactly the same thing, that we're taking the limit of our slope formula as delta x approaches 0. We can also ask for the same instruction in words, saying find the derivative or find the slope of the tangent. Everything on this slide means exactly the same thing. So for our first example, we're going to do a very simple, just finding the general form of the derivative. So to begin, all we do is plug in x plus delta x in the function the first time so that we get f of x plus delta x, and then just leaving our x in the second one. Make sure to protect that back function by parentheses because that negative needs to distribute. You've been doing this algebra for quite some time now, just to make the algebra easier for you. So now you're going to be learning, what does it all mean? So hopefully you're pausing the video and working with me as we do this. So you should be checking to make sure that you're getting the exact same fraction that I'm getting. As I distributed my negative and multiplied out my polynomial, we see that the 3x squareds cancel, and that the positive 4x cancels the negative 4x, and the 2 cancels the negative 2. As you can see, as I rewrote it, I factored out my delta x that was common in my 3 remaining terms so that I could cancel it in the denominator. So now I can actually take the limit as delta x goes to 0. I get 6x plus 0, because 3 times 0 is 0, plus 4. So my derivative, f prime of x, is equal to 6x plus 4. So what does this mean? It means that I have a general slope, because if I have this parabola and I were to have graphed it, you would be able to see that as I travel around my parabola, my slope changes at every point. And so the general form of my derivative allows me to have a slope that works absolutely everywhere on my graph. If I want to know what's happening to my graph at 1, then all I have to do is say, I want to find out what's happening at f prime of 1, and plug it in. So when x is 1, my slope would be 10. In this next example, we're going to be talking about the alternative form of the derivative. The alternative form of the derivative is used when we only want to study our function at one point. If we wanted to look at our function overall and be able to study it over and over again at many points, we would want to do the general form that we did in the first example. But if we're going to study one point and move on, then we can do the alternative form and get our answer directly as we do our limit. So as I start to plug this in, you should pause the video and go ahead and set your limit up and simplify your algebra to see if your algebra matches mine. Okay, so notice instead of plugging in x plus delta x, we were given a value of x being 3, and that 3 became our c to plug into our formula. So now that you have your algebra simplified, you should notice at this point that you can't plug in delta x equals 0, because that would make your fraction go undefined. So at this point, we're going to want to multiply by the conjugate of our numerator so that we can get our delta x on the bottom to cancel, and we'll be able at that point to plug something in. So as we multiplied by our conjugate, we were able to simplify our numerator. And when the tens subtract each other out, and we look at just the numerator of the 6 delta x squared, then the delta x is common, and we can cancel it out of both of those terms. And we're left with a numerator that is just 6 plus delta x, and we'll complete the rest of it. So now that it's no longer a problem to plug in delta x as 0, the delta x on the top becomes 0. Our middle term inside of our radical becomes 0. Our delta x squared becomes 0. And we have 6 over 2 root 10, which we can simplify and then rationalize. And our derivative, f prime of 3, is equal to 3 root 10 over 10. Now we're going to do an example of an application of using the definition of the limit to find the equation of a tangent line. So if I want to find an equation of a line, what do we need? We need a point and a slope. Well, our point, we're given x equals 4. And if we want to find our y value, we just need to plug in f of 4. And our slope, we need to take the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So plugging in for our point f of 4, we get 144. And so our point, when x equals 4, y equals 144. Now let's find the slope. Check to see how you plugged in your equation. We have 2x plus delta x cubed plus 4 times x plus delta x. That is our f of x plus delta x. Now we subtract our function, 2x cubed plus 4x, and we're putting all that over delta x, and we're going to take the limit as delta x goes to 0. So pause the video and FOIL this out, and come back and check and make sure we have the same equation. Okay, compare your algebra and make sure that it matches. We know that our 2x cubes will cancel and our 4x will cancel. And when we get that done, now we can take out a common delta x and cancel that as well. So taking our limit as delta x equals 0, our 6x delta x becomes 0, our 2 delta x squared becomes 0, and we're left with our f prime being 6x squared plus 4. Now we want to know what the slope is when x is 4. So we're going to plug in 4 into f prime. So we want f prime of 4, 6 times 4 squared plus 4. So now that we know that f prime of 4, when we plug in 4 into our derivative, we get 100. So that's m. So our tangent line will plug in what we have, y minus 144 is equal to 100 times x minus 4. And we get our equation of our tangent line is y equals 100x minus 256. Take a moment to copy down the examples that you need to do for the Google form. And there's one more thing I want to discuss with you. So let's just talk about one last thing, the relationship between differentiability and continuity. If our left limit is equal to our right-sided limit, then we say the function is continuous. It is also differentiable on the closed interval a to b. If a function is differentiable, then it's guaranteed to be continuous. But just because a function is continuous doesn't mean that it's going to be differentiable. A function must be continuous to be differentiable, which means it can't have any holes, jumps, gaps, no asymptotes. But the slope of the tangent must be the same on the left side as it is on the right side, which means we can't have any sharp turns which alter that slope so drastically. Let me show you what I mean. To study this function, we're going to take the limit as x approaches our value of c of the slope at the point of c. So we're going to take a look at the limit as x approaches 2 from the left and from the right. So simplifying these limits down, I get the absolute value of x minus 2 minus 0. So the absolute value of 2 minus 2 on both of these is 0. So we're taking a look at the limit as x approaches 2 from the left of the absolute value of x minus 2 over x minus 2, and comparing that to the limit as x approaches 2 from the right of the absolute value of x minus 2 over x minus 2. Now we know that we can't plug 2 in because this goes undefined. So let's take a look at this graph. When we can't plug it in, when we can't fix it, we need to take a look at the graph. So when x is approaching 2 and we want to look at what the table values are going to be, we're actually taking the limit of the slope. So logically, we can look at the slope on the left and say this slope is a negative slope, and if I looked at it as a line, this is a slope of -1. And coming on the right, this is a slope of +1. So I have a slope of -1 on the left and a slope of +1 on the right. If we were to just look at a quick table of values, anything that I plug into the numerator is going to be positive, but if I plug in anything less than 2, I'm going to be getting a negative value in this slope. So on this part, the limit as x approaches 2 from the left is going to equal -1. And if I plug in values over 2, then I'm going to get a +1 on the right. So the limit as x approaches 2 from the right is equal to +1. Because the two limits do not equal each other, then we say that the function is non-differentiable at x equals 2. And so sharp turns, any function that has a sharp turn where the slope has that drastic change, is not differentiable. So no holes, no gaps, no jumps, no sharp turns for differentiability. The final thing is your homework. Make sure you copy it all down. We'll be spending a couple of days on this so that you have a really strong understanding of this section. I'll see you tomorrow.